Good evening, and welcome to the 2007 Engineering Lecture Series. I'm Matt O'Donnell. I'm the Dean of Engineering, and it's great fun. Last year, during this series, I was out of town for all the lectures. This year, I get the chance to come, so I'm really excited to do this. This is jointly sponsored by the College of Engineering and the UW Alumni Association, and is part of the lifelong learning program with UW Alumni Association. We're letting these scroll through just as you were walking in as well, because this is truly a joint project between the Alumni Association and Engineering. And we hope that you, if you are not members of the Alumni Association, that you learn more about them. I think it's what? uwalum.com. It is .com. Okay. Want to make sure that it is a for-profit organization. Let's get to the talk. It's a great pleasure to do this because I'm Dean of Engineering, but I'm also a bioengineer myself. And a promise that we have had for a long time is this idea that in biology, could it be like other industries? Parts is parts, right? And the idea is can you look at living organs as something that can be replaced in the same way that another functioning part in a non-living system can be replaced upon failure? Buddy, I can't call you Professor Ratner. I'm sorry, I've known this guy too long. So it's Buddy for me. Is been a true pioneer in this area. His work, his fundamental work, has come in the area of biomaterials, but it's really pushing towards real clinical applications where the most excitement is. And excitement in this area is really investigating whether we can truly produce replacement parts. So it's a great pleasure for me to introduce Professor Buddy Ratner of Bioengineering. So please give him a warm welcome.
Well, good evening. What a great audience. Thanks everybody for coming out. Very much appreciate this. And I hope what I have to tell you will be of interest and excitement. The title of the talk is fairly obvious, Rebuilding the Baby Boomer, Replacement Parts for the 21st Century. And let's see, maybe we'll just start right here. It's kind of a glib slide, but when one thinks about some primitive time in the development of humans, I think from an evolutionary standpoint, humans just had to live long enough to pass on genetic material. Probably by age 18 or 20, you'd already made it a few times, had some progeny, and then this saber-toothed tiger beast could come along and consume you. And it really would make no difference in the evolutionary scheme of things. But so we were made maybe to last that long, 20, 25 years. Then you look at modern times. And a number I found for 2003, the average life expectancy in the US is now hovering 77.6 years, and that's an average. So a lot of people are going to live well beyond that. And what we find, living way longer than maybe evolution or nature had intended us to, is we wear out and we're easily damaged. A disease, just wear of joints and other parts simply wear out, and then these adventurous excursions to other lands and other forms of trauma. In fact, the trauma thing is kind of interesting and certainly enters into our thinking in this field. This is really a pretty striking slide. Call it compelling needs. And so if you look at the percent of injured soldiers that were saved in war, in Civil War, only 19% of the injured soldiers ever made it home again. But it's increasing with these wars. By the time we get to this Iraq conflict, 96% of our soldiers that are interested make it home. But what condition do they make it home in? This is where I think we're going to need some abilities to address the problems many of these individuals have. So the talk has baby boomers in the title, and I kind of use that as a theme to build around it. Kind of talks to the fact that a large segment of our population and some, I think, prominent baby boomers are illustrated along the bottom of this slide. But the generation has been defined as those born between 1946 and 1964. In 2005, we had 78 million of these baby boomers. In 2006, the number of people turning 60 each day, 8,000 people every day turning 60. Americans 65 plus will more than double by 2030. Boomers can expect to be grandparents for 40 years. That gives me a long run for being a grandparent. And the median consumer for Harley Davidson is a 46-year-old male, which I thought was kind of an interesting fact, too. So we have kind of an interesting aging population that are doing adventurous things that may require some repair. In fact, let's see, October 16th in the Seattle Times already, the first baby boomer applies for Social Security. So we're up there, and I probably could have put my picture on the bottom of that little slide, too. So if indeed the general population is aging, graying, all sorts of polite terms for this, but associated with aging, we come with a series of interesting heart disease, cancer, joint problems, vision loss, hearing loss, diabetes, incontinence, and then I like this old Czech expression, if you're over 60 and you wake up one morning and nothing hurts, you're probably dead. So I think we find ourselves wearing out. So most of the diseases of aging are associated with what I call the wearing out of parts, or sort of malfunctioning of tissues and organs. So we could think about maybe let's replace the defective part. Well, this replacement has certainly developed into a very successful engineering medical field called biomaterials and medical devices. I have a picture of a hip prosthesis here, and we'll talk a good bit more about these things. But what are the options for replacing wearing out and aging parts? So we have, again, biomaterials, medical devices. Many people talk about transplantation. Well, there's an interesting website there, and any moment you tuned in, I tuned in at 10/13/07 was the last time, and 97,000 people were waiting for transplant parts, just sitting there while they're potentially going downhill waiting for a transplant part. We don't have nearly enough transplant parts. So yes, this is a possibility, but probably will never be really successful. You can also envision a life with altered functionality. Some people find that satisfactory, but most of the boomers really want a life with full functionality. And then that leads to two things, tissue engineering or regenerative medicine. So what this talk will really focus on is these biomaterials and medical devices, this thing called tissue engineering, to give you a hint, it's sort of grow your own, and regenerative medicine is also in that category. So we can talk about the way history, or at least Hollywood, has envisioned kind of replacement parts. I think the Frankenstein monsters kind of entered the public consciousness, and then I always wondered about these electrodes in Feller's neck. And then also in the Wizard of Oz, we have a Tin Man. Again, an interesting vision. But a more modern, maybe, version of these ideas came from this man, Martin Caidin. Martin Caidin wrote, when he finally left us, wrote over 100 books. And check the web, you'll find lots of them. And he wrote in two subjects. He wrote in military aviation, and he wrote in science fiction. And he was one of these sort of bigger-than-life characters. I had the wonderful opportunity to know him, and he was just a huge, physically and personality-wise, just a huge individual. And he came up with this idea in a book called Cyborg, which was the novel that inspired this TV show, The $6 Million Man. Here's this character, Steve Austin, running faster than a locomotive in this particular show. Steve Austin was an aviator, and plane got into some horrific accident. He was taken to the secret military base where he was rebuilt with synthetic parts. And there were two interesting things about this show. Number one, Steve Austin's parts, replacing his natural parts, were not only as good or replacements, they were better. He was stronger, faster, had powers which ordinary people didn't have. And the other interesting thing was the engineers were shown as heroes, not as nerds. They were great guys in this TV show. So I always liked that. And that's sort of just on September 26th, the new Bionic Woman reappeared. I was actually at the Biomedical Engineering Society meeting, and I ducked out of a dinner to catch a little of this show. I don't think this is going to be a great hit. This was really an awful show. But this lady has parts like you wouldn't believe. I mean, she is really a terrifically powerful individual, given the prosthetic eyes, limbs that were given to her, again, in a similar scenario to the original Bionic Man show. And we have, again, this goes on and on, the RoboCop idea, a police officer who was damaged in the Call of Duty was rebuilt with prosthetic parts. And this particular movie, which apparently is in the movie theaters right now, and if anybody knows Quentin Tarantino movies, this has got to be pretty interesting. I have not seen it, but this lady also has some prosthetics we've never even imagined in our group. But finally, we get to the most distinguished of all science magazines, Science itself, and we find on the front cover this actually sort of an artist's creation of an individual with parts. And we can see that illustrated in this, we have an artificial ear or cochlear implant, lens reconstruction, heart assist devices, pacemakers, hands, hip joints, legs, quite a range of stuff. So we've gone from science fiction to reality very quickly in these slides. So let me tell you where we're going to go with this talk. This is sort of the roadmap for this talk. We're going to talk a little bit more about some of the needs and maybe tragedies that we can potentially address with these devices, and then bring that into opportunities of medical devices, talk about tissue engineering, the next generation, and talk a little about entrepreneurial thinking, which will help us get to these parts that I think fix and help people. So let me start again with some of these human tragedies or opportunities. One of the things I'll tell you about is a program we have addressing cardiovascular disease. And so in 2007, 80 million Americans, 1 in 3 adults, have some cardiovascular disease. Basically, 1 million people die each year of cardiovascular disease. Cardiac disease counts for 40% of all deaths. And this is a totally amazing fact. The cardiovascular disease claims as many lives each year as the next 7 leading causes of death combined. So yes, cancer is terrible. Yes, diabetes, horrible problem. These truly are horrible problems. But cardiovascular disease is the main thing that if we can make progress, we will have done some remarkable things. Here's another one. It seems so simple. This is infection. We sometimes call it device-centered, medical device-centered infection. And the sort of background of it is that a biomaterial that a medical device is made out of, a couple of bacteria stick to it, and they form kind of a slime film. They multiply on the surface and form the slime film. We call it a biofilm. This biofilm is very resistant to antibiotics. So 2 million US patients a year acquire infections in the hospital, and 90,000 patients each year die from infections in hospitals. Hospital infections are in the top 10 infectious diseases. You'll add $30,000 to your hospital bill if you get one of these infections. And we use something of the order of 250 million catheters per year, and 5% of these have this kind of slime film on it, this colonization. And interestingly, because of this slime film, it'll take 1,000 times higher antibiotic dose to kill bacteria in a biofilm than it does if it's just sort of floating in a test tube, floating in solution. So unfortunately, 1,000x dose of antibiotic will kill you too. So we really can't use that. But to some extent, things in hospitals haven't changed much from this illustration of some ancient hospital ward. The third human tragedy, opportunity to do some good, is one maybe people don't think as much about, but it's the esophagus. And this started in a project that was developed in Singapore through the University of Washington Singapore Alliance. But Asia has the highest rate of esophageal cancer. So in most Western countries, we have 3 per 100,000 esophageal cancers. In Central Asia, there can be 140 per 100,000, way higher incidence of esophageal cancer. Estimated 13,000 deaths now in the United States, but it's the fastest increasing cancer in the US. It's one of the deadliest forms of cancer, and the surgical prognosis, yes, they can take out the esophagus, but most people don't thrive without their esophagus well, and again, the prognosis is poor. So what we have is some opportunities, and what is our approach to address these pressing needs? Well, medical devices constructed of synthetic biomaterials, or living construct comprised of the patient's own cells. And how feasible are these ideas? Well, we're going to start with a little historical review and then get into some things we're doing right now. And we can start a long way back. We can start almost 4,000 years ago. And this is a toe prosthesis that was found in some crypt in Egypt. I've read articles where people are still wondering, was this used just in a cosmetic sense, or was it actually implanted? People aren't sure. In any event, people were thinking about replacing parts far back. The Egyptians also used linen sutures. So there's a long history here. In 100 AD, pretty near 2,000 years ago, they found the remains of this fella, and a wrought iron dental implant was found in the jaw of this individual. They x-rayed the jaw and found that it was osseointegrated. That's what we try to do today with the dental implant. It integrated into the bone in the jaw, this iron dental implant. They also said in this article, which appeared again in this prestigious journal, Nature, the implant was probably set by impaction soon after tooth loss. Well, that must have really hurt to hammer that thing in. But the fella did have a tooth for the rest of his life. And interestingly, the Mayans also used this inner layer, this pretty mother of pearl, in seashells, call it nacre, and they use this in tooth implants, and nacre actually heals very nicely into bone. So they were way ahead of their time there. But I like to sometimes put the more modern era with this particular book. So it was called The Culture of Organs, and it was by Alexis Carrel, who won the Nobel Prize in, I believe it was 1921, for figuring out how to sew blood vessels together. And he was working with Charles Lindbergh. And we know Lindbergh is an aviator, but Lindbergh was also an engineer. So we have a physician working with an engineer and describing a lot of things that look to some extent, not really look like, but function like modern organs and modern tissue engineering ideas. How can we keep organs alive? How can we grow cells into organ-like structures? How can we provide the nutrition? These were all in this very interesting 1938 book. Another one of the historical pioneers is this individual, Vellum Khalfa. I'm very pleased to have had the opportunity to know him. And Dr. Khalfa is quite elderly now, but still doing quite well and quite active. And Dr. Khalfa in the Nazi-occupied Netherlands showed that he could take sausage casing and a washing machine and dialyze the blood of patients and keep patients alive. It was quite a miraculous experiment, because at that time, if your kidneys failed, you spent 3 weeks in agony and then died, and there were no options. You just succumbed after 3 weeks of very unpleasant times. So Dr. Khalfa's medical miracle was remarkable. And these events all happened, let's see, we're talking now, so Dr. Khalfa was the first sort of modern ideas in medical organs. Happened maybe 50, 60 years ago. The end of World War II brought sort of new materials. They were war-restricted items to the public. And some of these items, nylon, the famous scenes of nylon being released from parachutes to the general public, nylon, Teflon, silicones, titanium, stainless steel. These were all released from the war, and suddenly people found them. And many of the people that found them were physicians who said, these materials have remarkable properties that have not been seen in the history of this planet before. So one of these individuals, this is Sir Harold Ridley, and Ridley was an ophthalmologic surgeon. Ridley worked at the British Air Force, and after the war he saw many pilots that flew these Spitfire planes in particular, and the windshield of the Spitfire plane was made of plastic, and there was an unfortunate accident that was very common for these individuals. is the machine gun fire during air warfare shattered these windshields, and many of these aviators got what we might call unintentional implantations of shards of plastic right into their eyes. And after the war, Dr. Ridley was looking into the eyes. The eye is a nice transparent window into the body. He looked into the eyes of these aviators, saw those splinters just sitting there, not doing anything. At that time, the conventional wisdom, you've got a splinter in your finger. What does it do? It gets red, it swells, gets infected. Here were splinters of material in the body years later, and he said, maybe these are biocompatible. So he literally went to ICI Corporation that made the windshield, got a sheet of the plastic, and fabricated the first intraocular lenses, implant lenses. And they kind of look like this. Here's a lens. It's a little smaller than, about half the diameter of a dime maybe in size. And they fit into the, we call the capsular bag. That's the bag that holds your natural lens. If your natural lens turns cloudy due to cataracts, they pop out the natural lens and just pop in one of these implant lenses. And this is going into 7 to 10 million humans every year, this particular device, based upon that observation with a windshield. Here's another individual, also British. This is a British orthopedic surgeon, John Charnley, who again knighted, as was Ridley, for his development. But he was also thinking about some of the new materials that came along, these stainless steels, these high-density plastics. And that led to the hip and knee prostheses that are so widely used today. And this one shows a titanium placed into the femur, and then another component placed into the pelvis. And these really work pretty well. This idea of orthopedic replacement, this just recently appeared in the Smithsonian magazine. This horse, Barbaro, is actually a very sad case. A Kentucky Derby winner. They expected the horse to win the Preakness, probably take the Triple Crown. It was one of the great hopes, this horse, and broke a leg in the Preakness. They fixed the leg with a plate and 27 pins, put the horse in a tank of water to take pressure off the healing. It healed, but the horse got infections from those, all that metal in him. And succumbed to the infection. So they had to put the horse down. But here's another device, maybe somewhat infamous, the breast implant. One of the most striking things, let's see, in 1980, 100,000 of these were going into women. You know, the device itself is remarkably simple, a silicone rubber bag filled with a silicone gel. It was one of the first modern implants in the way it was designed, but in 1980 we were putting 100,000 in. In 1992 the FDA declared a moratorium due to concerns for the safety of this. By 1996 the device had been absolved of the safety issues. The FDA admitted that there was no evidence that this was causing any problems, and the steady increase in the use is pretty striking. And it's a question I always ask. I just put it on the slide. The latest data I had of the 360,000 total, 40,000 are for mastectomy reconstruction, and the rest are cosmetic. So it's obviously a device that is wanted. Here's another simple one, but has made a very big impact, contact lenses. It's invented by this gentleman, Otto Victorly, actually an apparatus in his kitchen. But one of the interesting things about this is almost the first biomaterial that was designed specifically for an application. All those other things I showed you, stainless steel, titanium, silicones, these were all Teflon, nylons. These were all materials that were available already and were adopted for medical use. Here Dr. Victorly said what we need is something soft and that picks up water, a hydrogel, and really was quite a brilliant pioneer in inventing this contact lens. We have 70 million wearers worldwide, and one example, when Mark McGwire hit his 70th home run in 1998, he was wearing a yellow-tinted contact lenses. They're sort of like shooting glasses or ski goggles, increased the contrast, and they corrected McGwire's vision to better than 20/10. I guess people are up to 73 home runs now. I'm not sure if Barry Bonds has these lenses. But anyway, this is another interesting thing. These are contact lenses for chickens. And you might ask, well, why would a chicken got a hot date? Why does it need a contact lens, you know? And they're red. Well, it turns out when chickens are roosting, the farmers have them roosting to lay eggs. And two hens are sitting next to each other, and they kind of like to peck at each other. And if one breaks the skin of the other and they see blood, they all jump. They really are pretty fierce animals. They all jump on that bleeding chicken and kind of rip it to shreds. It's kind of barbaric, but I'm not going to comment on the way chickens live their lives. Anyway, they find if they put these red lenses into the chicken's eyes, they can't see the blood. So they're fine. They lay eggs. Here's another story. This is an act that was on TV when I was a boy, Winchell and Mahoney, a ventriloquist act. And Paul Winchell was a PhD, an inventor. He has a whole bunch of inventions, including a new type of corset, new fountain pens, things like that. But he also invented the artificial heart. And we can go back to Dr. Vellum Khalfa again, who did the artificial kidney. Khalfa, by this time, had moved from Amsterdam to the University of Utah and took actually asked Paul Winchell to sign the artificial heart patent over to the University of Utah, which he did. And that led to the Jarvik 7 heart, the first artificial heart to go into humans. And that has led to a modern artificial heart. If you had to buy one, you'd spend about that money. That's what they're selling for these days, these models of artificial hearts. This is called the heart assist device. They leave the natural heart in, even though it's failing, and just assist it with pumping. It's much less traumatic surgery to do it that way. And here's the power supply. And this is an interesting thing I found in the Straits Times, which is the newspaper, the daily newspaper of Singapore, of this little girl pushing a power supply, and she has a heart assist device on her, probably waiting for a transplant to come along. One of the interesting things about these are hardly fully developed devices. They have loads and loads of complications, including infection, blood clots, the fact that they don't pump the blood quite right. But there's a lot of stuff to read here. But basically what it says, they did this clinical trial and found that based upon the best therapy they knew how to use for people with failing hearts, this thing did much better. It had a 52% chance of surviving a year compared with 24.7% survival for patients who were on the conventional therapy. So they could double the number of patients that survived using this device, even though it had problems. So the FDA has approved these for that reason. Well, that leads kind of the modern biomaterials field, and what we find is that, and again, I'm not going to read, there's a lot of detail on this slide. I actually base a whole lecture in one of my classes on this slide. But different medical devices, and the numbers are hundreds of thousands of millions. These devices save millions of lives, and the quality of life is improved for millions more. And these are yearly numbers, by the way. If they didn't work, we wouldn't be putting them in again. We put them in year after year. They do work. So that's a pretty good record for what we developed from that primitive World War II stuff. But there were problems, too. And again, this is another complicated slide. But it lists, again, pretty much the same list of devices. And we can look at the intraocular lenses, those eye implants. So yes, they do correct your vision or give you sight after the cataractus natural lens is removed. But there's a 25 to 50% reoperation rate on these lenses. That's a huge trauma for the patient, huge cost for the healthcare system. Hip and knee joints fail at 10 or 15 years. We can't use them very well on young people. Blood vessels, vascular grafts we call them, fail due to thrombosis. They don't heal well. Heart valves have problems. It goes down and down. We have major problems with our medical devices. Yes, they save lives, but there's a lot of room for improvement in these devices. One of the areas we've identified where improvement would be needed, this is a picture of a device that's been implanted for 6 weeks. It's been implanted for 6 weeks, and the device is a Teflon glucose sensor. If we could implant a glucose sensor in your body, diabetics would not have to do these painful finger pricks and could have better monitoring of their blood glucose. But what happens to this device in all humans and animals, for that matter, is that the body puts a dense collagen capsule, a dense bag around it. The FDA may consider this Teflon device biocompatible or again, have an approved material here, but the body just sees it as a foreign material and puts a wall around it. And so you've got to get glucose to that glucose sensor. This is a pretty dense barrier to try and get that through. And we believe this is one of the major problems that can lead to complications with a lot of those devices. The body walls them off. Let's see. Where are the opportunities in biomaterials? Well, I'm going to tell you now about biomaterials that heal instead of getting it walled off in that tough capsule. Infection-resistant materials. I think there's huge opportunities in neural electrodes, especially if we can keep them from being walled off from the body. Targeted drugs, powerful diagnostics, and tissue engineering. And we're not going to do all of these, but we'll do some of these. So we've had a program at the University of Washington generously funded by the National Science Foundation for the past 11 years. It's called UWeb. It's an engineering research center. And UWeb had a very simple focus. It said today's biomaterials, now the body puts this capsule, this bag around them, isolates them. What if we could take a biomaterial, treat the surface with some coating that the body would see, would recognize, would say self, and heal it into a natural vascularized site? We call these biomaterials that heal. And the UWeb program had some 20 professors, 100 students, 20 or more companies in partnership to evolve these biomaterials that heal. And we believe we've succeeded. We invented a type of materials, one of the many projects that came out of UWeb. But it basically looks like this. Now, these little cups, these are little pores, they're spherical pores. And these dark areas are interconnects between the pores. So if we went through this little hole, one layer down, you'd be in a spherical chamber. But the size of these chambers are about 1/2 the diameter of a human hair. So this is a pretty big magnification. But the interesting thing is when the spherical pore size is just right, the pore size is too small, we find the biomaterial gets this capsule around it. The pore size is too big, the biomaterial gets this capsule around it. If it's just right, the materials seem to heal into this vascularized sort of capsule. Let's see, and these are the biomaterials that heal, and a sphere templated porous scaffold is what they are. Here's another material. It's a similar thing made out of the same kind of materials, and again, you can see these interconnects into the cell a little better. I always like this picture because, by the way we cut it, got a Mickey Mouse here. So, and these are another biomaterials that heal. So we think we have taken a material I don't think anybody's ever seen in the history of the world, a synthetic material you could put in the body that becomes integrated. And we are taking this, I think, out to the real world of medical devices, working with an ophthalmologic surgeon, we're working with an orthopedic surgeon, we're working with a gynecological surgeon, all to try and use these materials in surgical repair. So this is happening right now. Let's talk about infection resistance. We're using a material called a polyurethane. The polyurethanes are what they make these artificial hearts out of. It's the pumping bladder. If you want to know what a polyurethane looks like, look at the soles on your running shoes, in fact, on almost any shoes. If you have kind of a black rubber on the bottom of your shoes, it's probably a polyurethane. It's a tough polymer. And we make medical devices out of it. So we took some polyurethane and we flowed, this is with Professor James Briers, a professor in bioengineering at the University of Washington. We flowed over the surface this bacteria, Pseudomonas aeruginosa. This is a biofilm-forming bacteria. It's a nuisance in surgical suites. It's one of the big problems. And this bacteria was kind of treated so it glows green. And you could see at 24 hours, the polyurethane is just glowing green. So we invented a form of polyurethane that slowly releases ciprofloxacin antibiotic. And now we're flowing these bacteria over, and there's essentially none on there. You can see this is an assay where the bacteria turn red when they die. They're green when they're alive, turn red when they die. And you can see some red ones, and these green ones probably will turn red when the Cipro poisons them. So we can now make materials, we think, that really do resist this bacteria. Here's another way we do it. This is with another one of our professors called Moringer from our electrical engineering department. And in this slide, we've taken a new kind of material that prevents bacteria from sticking. They just can't attach. And what we've done is made sort of a test sample here where everything inside the dotted lines, see these dotted lines? Everything inside is bare glass. Everything outside the dotted lines is our special treatment that prevents bacteria from sticking. We put some bacteria on the surface. 70 hours later, where do we find the bacteria? On the bare glass, not on our material. So our material is very effective in keeping bacteria off. Okay, so that's some things we're doing in medical devices. We've hit two of the opportunities, healing and bacterial infection. Here's another one, I said electrodes. So at the moment, quite a number of people are getting these electrode arrays that are put right into the cochlear and allow a person that really has lost hearing functionality to hear pretty well, to talk on a telephone, to appreciate music. These are relatively common, and there's an external microphone and an internal implant right on the cochlea that stimulates the cochlea. These work pretty well, but there's another kind of implant that's coming along, and this was sort of glibly illustrated in a cartoon that was in the International Herald Tribune. This monkey has an implant in its brain and can control the cursor on the computer screen without ever touching a mouse. Now, that seems like a great innovation, and in fact, actually, this is just a Photoshop recreation, but the reality is, make jokes about it, this fellow has one of those electrode arrays in his brain. He's a quadriplegic, and he's able to control the cursor on the computer screen from this electrode array. The problem with these electrode arrays is they need a very intimate contact with the brain to do this. And what does the body do to implants in the body? It puts this capsule around it. These devices stop working. They work initially, and then they cease working. So this would be fabulous if we could have that working. We could have people, somebody with a quadriplegic, using their mind to control a variety of artificial limbs. This would be a spectacular advance if we can get these devices to function for long periods of time. You don't want brain surgery every month. That's not good. So to fix that chip. And the University of Washington is very lucky to have many of our people at College of Engineering. Professor Yoki Matsuoka just won the immensely prestigious MacArthur Award, the Genius Award. And Professor Matsuoka works on this concept of how do we, from a computer standpoint, translate those flickering signals on the brain into things that can control limbs. So at the University of Washington, we're lucky to have teams that work on so many of these different projects. Talking about limbs, I thought this was interesting too. Some guy smuggled iguanas into the United States in a hollow leg, but we won't go into that. Okay, here's another project that I'm actively working on with Professor Mark Humayan. Mark Humayan's a PhD electrical engineer and an MD ophthalmologic surgeon, and he is putting a chip on the retina. And he's taken people that haven't seen anything, have not seen a flash of light in 50 years, and they can take this chip. The chip just has 16 elements in its first version, but quite a few humans have these now, and they can tell where a window is or a door is. They can distinguish a plate from a fork, and they haven't seen a flash of light in all these years. And again, this involves a direct electrical stimulation of the retina. There's a video camera outside the eye, and to use these, there's two biomaterials interfaces that are very important. There's a skin wire interface to get that wire from the TV camera in, and the retina electrode interface. So there's biocompatibility problems too in this device. Here's another innovation that is, I think, very important area in biomaterials that, again, I think represents some things that are coming out from our College of Engineering. Professor Paul Yeager has developed, with his company, Micronics, has developed some very remarkable chips on a card. These are low-cost disposable chips. They're a complete lab on a chip. You can put a drop of blood in one end and get a whole bunch of assays out. And because of the potential to diagnose disease in the third world, Professor Yeager has won the Bill and Melinda Gates Challenge Grant for this biomaterials development. Okay, so let me finish up with tissue engineering. We're pulling into the home stretch here. And people are talking about not just putting in synthetic materials and artificial parts we've talked about to date, but growing just about everything from hair down to digits or fingers and toes, and just about everything in between, as you can see from this extensive list that I'm not going to read. Is this real? Well, now at least 9 humans have a bladder that has been grown from their own cells. They were born with bladder defects, children. They were destined for a horrible life, but thanks to this ability to grow a bladder out of their own cells, they have living bladders back, and some of these children are doing very, very well. And this is from the Washington Post, pretty recent, April 4th, 2006. And the company has gotten phase 2 FDA trials, which means it's well on its way. So yes, we can regrow organs from our own cells. One of the projects we're working on is if you have a heart attack, a portion of the heart muscle dies. It never reheals. It usually sets you on a downhill spiral. And we've been awarded a grant from the NIH. It's a 10-year NIH-funded grant to rebuild injured heart muscle. This dead portion will never regrow, and we're working on doing that. How are we going to do that? We take a synthetic material scaffold. Again, we're still using some biomaterials. We seed on some interesting cells. We allow them to develop. We're going from the test tube in vitro to in the body in vivo. Eventually, this tissue sort of develops. We implant it, gets blood vessels grown in, and ultimately fuses and integrates with the heart. This is actually pretty easy to do in PowerPoint. It's a little harder to do in reality. But what this is a movie of that sphere templated material you saw, that material that seems to heal so well. It even heals well in heart muscle. And what we've done is seed this with living heart cells, cardiomyocytes, and they thrive and they beat in this material. And we're now taking this along. I think we're well on our way to achieving our 10-year goal to make pieces of replacement heart muscle that will allow surgeons, for the first time in history, to restore an ailing heart. So this is very exciting work. Another way people are doing this tissue engineering, it's an idea called cell sheet engineering. We can grow cells in a dish. We do this pretty easily. And we've built some dishes that have a special coating on them. This is an invention we did here, where cells grow at 37 degrees. That's 98.6 body temperature. That's the temperature cells grow on. Just take it out of the incubator at 98.6 to room temperature, and the cell sheet spontaneously detaches. You can take the cell sheet and start stacking them up and building tissues, which are multi-sheet constructs. And this is actually what you're going to see here is we've gone from the cells in an incubator, put them on the microscope stage and looked at them. So they're going from the 98.6 to roughly 70 to room temperature. And what's going to happen as this cools down is this sheet of living cells is going to spontaneously detach. So we'd have a sheet of living cells of the type of cells that line blood vessels to make an organ out of. This idea has been used for cornea. It was actually invented by this man, Taro Okano, from Tokyo. And the idea has been used in corneal surgery, and the country of Japan actually issued a stamp in honor of this particular work that Dr. Okano did with cell sheet engineering. Here's another example of a novel way to do tissue engineering. This man is Thomas Boland. He got his PhD from the Department of Chemical Engineering here about 1990. He's now a professor at Clemson University. And he invented the remarkable idea of filling the cartridges in an inkjet printer with living cells and printing tissue. So this way, you take a CAD-CAM diagram, a CAD-CAM computer map of a tissue, feed the CAD-CAM information to the inkjet printer, spit out the cells, and build a living tissue of cells and polymers. And he's doing this. He's shown that he can build blood vessels this way. And Professor Boland has started a whole field of this concept of cell printing, as many people call it. Okay, the final object is the esophagus. I mentioned that. We have an esophagus project. This is what the esophagus looks like. If we're going to tissue engineer, make an esophagus, we have to recreate this complicated structure. Here's where the food goes. There's muscle layers, there's blood vessels, here's more muscles. Actually, this isn't a muscle, this is a mucus layer. There's this basement membrane of cells that's very important to the functionality. Here's the muscles. You have muscles that go longitudinally and muscles that go radially. Pretty complicated structure to make. But we have a program funded that has been funded through A-STAR, the funding agency of Singapore, and we're working with Singapore because this is so important in Asia. We call it our Esophagus Roadmap. How do we get the cells to line this way? How do we get them to go radially? How do we do this lining, this mucus layer lining? This is all happening, and this is another project that's going on here. So I got this email the other day. Hello, Dr. Ratner. I'm a kidney transplant patient with kidneys failing. I'm very interested in volunteering to test a kidney built from my own cells. And so he heard one of my Science Forum talks and wants me to build him a kidney. That's, it's very neat that people are excited about this. I hope everybody is excited about this work. But it leads into the kind of very last section of this. There's many ethical issues in this biomaterials and tissue engineering, such as how we put these things. What happens when you put the first ones of these into humans? I think those first bladders were amazing experiments. And then there's many issues, of course, ethics issues of animal experimentation, scarce allocation of resources. What happens if we don't have enough of these to go around? What about implants that are better than the original part? What if people wanted? You could make a better one. People would go and say, I don't need this flesh arm. Give me one of those better ones. This seems to enter into a whole new realm of ethics. Cosmetic implants gets into really strange territory given what some people do to their bodies. And also research and physician financial involvement. Most of this comes from professors, and professors have a stake in this. And we would not want to be unethical. So let me get into the final part, which is entrepreneurship. And my own personal philosophy is nothing is accomplished in the real world unless it is adopted by industry. Because I can never make a device. Those bladders are being made by a company that are going into children now. I could never make one to the standards that have to go into hundreds of thousands of humans. I have to team with a company to do this. So academic scientists don't manufacture devices. A paper in the journal Science cannot save lives. I ask how I can repay the taxpayers who have supported this research. So I always love this quote, Prime Minister Gladstone on a visit to the famous scientist Michael Faraday's laboratory, asked him whether this esoteric substance called electricity would ever have value or practical use. And Faraday replies, one day, sir, you will tax it. And I think these things do develop into industries and all. So we asked the question, with time, how do we go from concept, feasibility, development, scale, clinical trial, launch? We have, going up this, the costs go up, the flexibility to make changes goes down, and we have what something either called the valley of death or the black hole of commercialization. With a smart academic idea, the concept never gets into the commercial things because of the high expense and difficulty getting through that. So we think a lot about barriers to get ideas to the clinics, university naivete, risk aversion, technology barriers, the FDA, reimbursement issues, physician conservative. How can we get over this wall and get to that patient? And kind of a new model is the professor entrepreneur. So at the university, maybe with angel investors, with foundations, federal government, get some professional management, and suddenly you have a corporation that's making these devices. Again, easy to do in PowerPoint, but trickier in real life. And yet, here's just this is a short list of some of the companies formed in more recent years by our University of Washington College of Engineering. Why are these companies formed? These companies are formed to get these clever ideas from the university out where the taxpayer can benefit. When it's a paper in Science, people don't benefit. If we can get it out faster, speed it on, people will benefit. So we know these dramatic increases in life expectancy. This projects to 2050. Life expectancy seems to be going up steadily. And us baby boomers, in fact, most people strive for good health, vitality, quality of life. Just being alive is not quite enough. We want these things too. And I think some of these innovations that I've told you about are going to help us achieve this health, vitality, and quality of life. So the remarkable innovations in medical devices, technologies, and diagnostics can help us achieve this if we can transcend this black hole of commercialization. With that, let me thank my funding agencies, the National Institutes of Health, the NIH. I'll also thank A-STAR in Singapore, but mostly students, staff, colleagues, and the College of Engineering that I think has served as a terrific platform to allow us to do some very interesting things. Thank you very much for your attention.
Thanks a lot, Buddy. So we have time for questions and answers. Let me start it rolling, Buddy. Tissue engineering as a promise has been around for a long time, right? And I still think the vision is the idea of a complete functioning internal organ as a goal. What do you think is the first target? Which fully functioning internal organ do you think is the first target for?
Well, again, we have these bladders, so they kind of.
That's true. That's
now
true.
They're not fully functioning. Let me just say, when they use this bladder surgery, they leave the sphincter valve in place. That's the natural one, because they can't tissue engineer that yet. But they do have a living cellular organ that gives the patient the sensation of fullness I have to avoid, and functions in every way that it's supposed to. So this is a clear example of the first one. I think we'll see things, a lot of people working on bone tissue engineering. There's many places we have to replace big chunks of bone. And people are working on this now, and since bone is one of these organs that does have some regenerative capacity, when you break your bone skiing, it heals pretty well. Bone is, I don't want to call it a low-hanging fruit. I don't want to trivialize the difficulties, but it's happening. Cartilage is another one that's happening right now. So these will probably be the first. Full heart is going to be very difficult to do, but we can dream.
Okay, great. So let's get into some of the questions from the audience. Does your work include any students from the UW Medical Engineering program?
We have a master's in medical engineering. A number of these students have come into our biomaterials program to do research and get a more advanced degree than this master's in medical engineering. So I have one of the students who've gone through that whole program, actually very interesting history because he worked in medical device companies throughout the Puget Sound for many years, took this master's program in medical engineering, took my course, really liked it, and now he's one of my PhD students working on these implant electrodes that I talked about. So yes, absolutely, the students do it. They do have opportunities. We also have students, of course, within my group, I have students from bioengineering, from chemical engineering, mechanical engineering, and at least one other engineering department. So it's actually pretty ecumenical from an engineering sense.
So is work being done on stimulating existing cells in the body to repattern and regenerate themselves?
Yes. Yes is the answer. We had a project, again, with one of my graduate students for some years to see if we could take heart cells and interestingly, when you're born, your heart cells stop multiplying. You have essentially the exact number of heart cells you had on day one when you were born. Pretty much by day two, heart cells don't multiply anymore. Your heart cells are much bigger, but you have the same number. So when you damage them, they don't go anyplace. So we had a project and see if we could do what's called get cells into the cell cycle. And we showed some hints of success. Actually, it would be a very difficult project for a graduate student because it's a very high-risk project. But he did show that you could start to do that. Other people have shown some hints of this. And I didn't talk too much about this, but the idea after tissue engineering is regenerative medicine. Can we get a limb to regrow? So an infant, a child under 2, can lop off the first joint on the finger, and the finger will grow back perfectly. Why do we lose that? Where does it go? That infant can do it. This salamander can regrow the tail perfectly. Why do we lose that kind of ability? People are working on that. A lot of people are thinking about that. And I think after tissue engineering, we will have true regenerative medicine where people actually might know how to get cells back into the cell cycle so they multiply, how to get tissues and organs to recreate.
Okay, and I'm going to end on this one, and it's a very good topic and highly germane to the subject, which is, do the restrictions on stem cell research limit your options in bioengineering?
The answer is yes. We have tried from adult cells to grow heart cells and have never succeeded. The place we've succeeded is in one of the George W. Bush approved embryonic stem cell lines, which we're using now. Unfortunately, that line, yes, we can make now buckets of CAR T cells. It's never been done in all of history. Professor Chuck Murray, who's in bioengineering and pathology, has worked this out. It's part of our BEAT program, but we need human embryonic stem cells, and we can't use the George W. Bush lines because these were grown on mouse cells, and so they're contaminated potentially with viruses and things like that. We have a new development in the state of Washington. It's an Institute of Stem Cells and Regenerative Medicine. It's happening down at South Lake Union. They're building a facility that will use not one penny of federal money, so the state of Washington can have real developments in stem cells that hopefully will get us on to therapies that can help people.
Let's thank Professor Ratner one last time.